Chapter 40, Introduction to Quantum Physics. We have learned in the previous chapter what happens when an object moves at relativistic speeds, and that is we have to use relativity to replace classical mechanics or classical physics in general. But in the introduction, we learned that there are two major areas where classical physics fails, and high speed is only one of them. The other one is the world of the very small, and that is the microscopic world. And this is where quantum mechanics comes into play that replaces classical physics. As a matter of fact, most of this course, Physics 1D, is dedicated to the study of quantum mechanics instead of relativity. This is our first chapter in which we introduce the basic ideas of quantum physics. So, quantum physics was first introduced in the early 1900s based on a series of experiments, and it involved a number of brilliant physicists. Einstein was one of them, and there is an entire series of theoretical and experimental discoveries in the early part of the 20th century, and what I have done here is I made a small table of events relating to this chapter. So here is physics around the year 1900. In 1901, Max Planck made the so-called quantum hypothesis, as we'll see in our next example. This was done in order to understand the strange behavior of what's so-called black body radiation. In 1905, Albert Einstein, the same Einstein, applied the concept of quantum hypothesis to photoelectric effect, which we'll also study. 1923, Arthur Compton studied the so-called Compton effect. Now, the photoelectric effect, you will see, is the so-called particle nature of waves. So is the Compton effect. There is another experiment done in 1926 which displayed the so-called wave nature of particles. And somewhere in between 1923, a French physicist by the name of Louis de Broglie proposed the so-called wave-particle duality, which unified two aspects of these different types of experiments, the particle nature of waves and the wave nature of particles. So he proposed what's called wave-particle duality, which plays a central role in our understanding of the quantum world. And in 1926, also, Erwin Schrödinger proposed the Schrödinger's equation for the wave that was studied before in the so-called wave-particle duality. And because of the wave nature of particles, you will have what's called uncertainty principle that was first discovered in 1927 by Werner Heisenberg. So we have a whole series of exciting discoveries, both in theory and experiment, and we'll study all of them in this chapter. So exactly what does the word quantum mean, and where does the word quantum mechanics come from? The word quantum refers to the quantization hypothesis or quantum hypothesis. And that was first introduced by the German physicist Max Planck in trying to understand the so-called black body radiation. So this is our first example of how quantum mechanics works. What is a black body? Well, if you look at an object, say, oh, it appears to be black. The reason why it appears to be black is because it does not reflect most of the light that's shining upon it. That's why we call it black. Now, there is no such thing as a 100% black object because anything will be at least partially reflective. A black body refers to an idealized object such that whatever electromagnetic radiation that shines upon its surface will be totally absorbed. It does not reflect anything back. That is called a black body. There is, of course, no such thing as ideal black body in the real world, but as an approximation, what we can think of is a cavity with a small hole opening to the rest of the world. And suppose I have a beam of light coming in, it goes through into this very small hole. It will be reflected multiple times inside. And because the hole is so small, it has very little chance of bouncing back immediately. And therefore, the light, once gets inside, gets trapped inside. That is, it never gets reflected, therefore we call it black body, right? Now, does that mean the black body can only absorb energy and never radiates energy back? No, because if that were the case, then there will be an inner energy influx constantly into the black body and no energy ever leaves it. And as a result, the temperature of the black body will rise forever, reaching infinity. That doesn't happen. In reality, a black body not only absorbs energy, it does re-radiate energy back, and the amount of radiation depends on the surface temperature. If initially its temperature is quite low, so it receives more energy than it radiates, then as a result, there is a net influx of energy, so the temperature will rise until the temperature of the black body is so high that it radiates the exact same amount of energy back as the amount of energy it receives. Then we say it has reached thermal equilibrium. Its temperature will no longer change. So, experimentally, what did people find when a black body reaches thermal equilibrium? Well, there are several things. One is, what is the total power emitted by this black body? It turns out that it satisfies the following formula. Sigma A E T to the power 4. This is called Stefan's law. And this constant, sigma, is called Stefan-Boltzmann constant. A is the total surface area. E is a number. And it's anywhere between 0 and 1. When it's 1, it's an ideal black body, so we're going to just keep it as 1 here. And T is the surface temperature of the black body. So a prominent feature of the Stefan's law is that the black body radiation power is proportional to its absolute temperature to the power 4 on the surface. And another prominent feature is that even though there are all kinds of radiations back from the black body into the environment, all kinds means all kinds of different frequencies or different wavelengths. The most prominent radiation, the brightest radiation, the strongest radiation happens at this wavelength. This wavelength is equal to a constant divided by the temperature of the black body. So you see, as the temperature increases, the most prominent wavelengths of radiation decreases, which means the prominent radiation shifts to a shorter and shorter wavelengths or higher and higher frequency. This is known as so-called Wien's displacement law. And to summarize both of them, we can measure the amount of black body radiation per unit wavelengths. And what you get experimentally is something like this. At very low, very low short wavelengths or extremely high frequency, the radiation has 0 intensity, and then it rises, and then it falls. It's like this. Nice and smooth formula. It is like an asymmetrical bell curve. It's not symmetrical. And what is the prominence of this wavelength? That's, of course, lambda maximum. So this is where the strongest radiation is emitted. And again, this I, lambda, is the amount of power radiated per unit wavelengths. So I, lambda, is defined as dP d lambda. Okay? And how do you get the total power emitted? Well, the total power emitted, of course, is the integral over dP, and therefore P equals to I lambda d lambda, going from 0 to infinity. And by definition, this in fact is the total area under this curve. You can think of this as an experimental finding. I have here some better drawing. Intensity, I as a function of the wavelengths. We have here different colors representing the black body radiation at different temperatures. See here, the temperature is 2000 Kelvin, and it goes to 3000, goes to 4000 Kelvin. As a result, the total area under the curve increases. That's because the total amount of radiation goes like temperature to the power 4. Another thing is that the peak frequency or peak wavelength also changes as the temperature of the black body changes. As you see here, going from 2000 to 3000 Kelvin to 4000 Kelvin, the most prominent radiation frequency increases, so the wavelength drops. The wavelength at the peak drops. It becomes shorter. So this is the summary of experimental finding. And the problem is, these experimental findings conflict with the prediction of classical physics. So where does the conflict come from? In fact, the conflict does not only exist, it's very prominent, it's in your face, it's so bad we call it a catastrophe, or more precisely, the so-called ultraviolet catastrophe. To understand that, what we want to do is we want to calculate the so-called energy density in the black body first, from a classical point of view, and let's see how it conflicts with our experiment. What is energy density? That is the amount of energy inside the black body per unit wavelengths. If the total energy contained within the black body is U, then you take du over d lambda, lambda being the wavelengths, you get what's called energy density. Let's see how we can calculate that. For simplicity, let's say the geometrical shape of this black body, the box, the chamber, the empty chamber, is in the shape of a rectangular box. And the side length of this box is L. Remember, I have electromagnetic waves that fills the interior of this box. This is the edge of the box. This is where the electromagnetic wave has zero amplitude. So you have a wave coming in, and the wave will get reflected on the surface. It bounces back. So we got a wave going this way, another wave going that way. The result is, of course, a standing wave. And I can draw a standing wave pattern. We have seen that in physics 1b, by the way. So here's an example of a standing wave pattern. In this particular case, I drew 3 loops. You can have 4 loops, 5 loops, however many loops, but you can only have an integer number of loops, right? Only an integer number of loops. And so therefore, the wavelengths lambda must be related to the length L. Lambda over 2, as you know, is the length of each loop. If you multiply this by n, you get the length L. We have learned that in 1b again. This wavelength cannot be just anything. It cannot be just anything. It must satisfy this formula, n being an integer, 1, 2, 3, 4, and so on. And from that, we can then calculate the corresponding wave vector in this direction. So the wave vector is 2 pi over lambda, as we know. And since lambda is given by L times 2 over n, 2 pi over lambda equals this, n pi over L. The corresponding electric field can be written as E maximum, which is the amplitude, sine kx cosine omega t. Right? That's the standard expression for a standing wave. And indeed, this expression is 0 at x equals 0. It is also 0 at x equals L, because when k equals n pi over L, when you plug in x equals L, you get n pi. Sine n pi, of course, equals 0. So indeed, it's a standing wave. Now that is a standing wave in the x direction. Remember, the box is 3-dimensional, so it must be a standing wave in the y direction and z direction as well. In fact, this is only the x component of the wave vector, k1, and the corresponding integer is n1. You should also make sure that the wave is also a standing wave in the y direction and z direction. So you have k2 and k3. These are the y and z components of this wave vector, and therefore the total wave vector is k1x, k1i times k2j. K2 is the y component of k, and then k3 the z component. And k1 is n1 pi over L, n1 pi over L, that's I, and n2 pi over L, that's J, and n3 pi over L, that's K. And this tells us that only those waves whose wave vector satisfies this expression can exist inside this chamber. This is because of the boundary condition. That is, the wave must be 0 at the edge of this chamber. We have not reached quantum hypothesis yet, even though you see there are already some discrete numbers, n1, n2, and n3. But those are nothing new. We saw them before. n1, n2, n3 are, again, integers. In fact, they are natural numbers, 1, 2, 3, 4, and so on. And if I were to plot the k vector in a so-called k space, I have x component, y component, z component. I call it k1, k2, k3. Let's change it to kx, ky, and kz, the same thing. You will find that if you do a drawing of the k vector, the end point of the k vector, which is given by this coordinate, this coordinate, this coordinate, cannot be just anything. It must be at a certain number of discrete locations, right? Discrete locations, because n1, n2, n3 are only integers. They cannot be just any number. So the tip of this k vector must fall at one of those dots. Each of the k vector represents a certain state, a certain type of electromagnetic wave. And if you look at neighboring dots, the separation between this dot and next dot, in this case, they only vary in the y direction, and then you have n2 differing by 1 unit here, right? Say this is n2 equal to 3, this must be n2 equal to 4, this must be equal to 5, and so on. So the gap in the y direction for these two k values, delta ky, would be delta n2 times pi over L. Delta n2 equals 1, so that's pi over L. This is the gap in the y direction. The gap in the x direction, also pi over L, so is the gap in the z direction. And therefore, if you look at the space occupied by each of these dots, the space, the volume in the k space would be delta kx times delta ky times delta kz. That's the product of these three, and then we get the volume of pi over L to the power 3. What is that again? That is the volume occupied by each dot. Okay? Now, if you wonder why we're doing this, it's because we want to know between the frequency f and f plus df, just how many of these dots are available, because each dot, you can put a wave on it. As a matter of fact, each dot, you can put 2 waves on it, because each dot only tells you what the wave vector is, but given the wave vector, which means it propagates this way along the wave vector, the electromagnetic wave can have 2 polarization directions. It can polarize in this direction, or it can also polarize in that direction. These are 2 distinct waves. So each k vector, you can have 2 different types of waves depending on their polarization. So let us take a look at the following question. Between k and k plus dk, k and k plus dk, if the k vector magnitude varies between k and k plus dk, how many of these dots are there? Each dot, of course, can accommodate 2 different electromagnetic waves, right? Now, between k and k plus dk, what kind of geometrical region are we talking about in a k space? Well, if k is a constant, the magnitude is constant, we're looking at a shell, right? A spherical shell. So between k and k plus dk, that is a region of a spherical shell whose radius is k and whose thickness is dk. So we're looking at something like this. This is part of a sphere, and the thickness is dk, right? This thickness is dk. So this is dk. My question is, in this region, this is the region, the highlighted part, how many of these dots are there within this region? Each dot representing 2 electromagnetic waves. That's easy, because all I have to do is to find the volume of this region divided by the volume occupied by each dot, which is right here, right? And this gives me the number of waves that can exist between k and k plus dk. Each wave is a simple harmonic oscillator, or a mode of the simple harmonic oscillation. So we then get the following. We get the number of simple harmonic oscillators whose frequency is between f and f plus df. We call that number dn. First of all, there is a 2 here because there are 2 polarizations. And then you take the volume of this spherical shell. How do you find the volume of spherical shell? Well, if it's an entire sphere of thickness r, then the volume would be 4 pi r squared times dr, right? Here, I don't have an entire sphere. I have everything. All these k values must be positive because all these n's must be positive. And therefore, I only have 1/8 of the volume of a spherical shell. So 1/8 of a spherical shell, which is 4 pi k squared, k being the radius, and then dk being the thickness, right? This is the volume of the spherical shell, divided by the volume occupied by each dot, or each mode, which is pi to the power 3 over L to the power 3. L to the power 3 is just the volume of the black body. And so this is what I get. I get V times k squared times dk over pi. But remember, I want to turn k into f. I want to figure out how many oscillators can exist between f and f plus df, f being the frequency. K equals 2 pi over lambda, and that is 2 pi times speed of light, or speed of the wave, c, divided by the frequency, and that is 2 pi over c times f. So you replace k with f by multiplying by 2 pi over c, so that's v over pi squared. There's a k squared dk overall. There are 3 powers of k, so there are 3 powers of 2 pi over c. Replace k with f now, f squared df. So the answer is 8 pi v c to the power 3 f squared df. What is this again? This is the number of oscillators, or electromagnetic oscillation modes, whose frequency is between f and f plus df. We keep that in mind. Now, we're halfway there. We know the number of oscillators that can exist between f and f plus df. But what is the energy of each of these oscillators? Well, in classical physics, in classical statistical mechanics, we learned that if you can express the energy of a system as a whole bunch of independent quadratic terms, then according to what's called equipartition theorem in 1b, what is the average energy of any quadratic term in the energy expression? Well, that's 1/2 kT, isn't it? And then for a simple harmonic oscillator, I actually have 2 terms. One is the kinetic energy term, the other is the potential energy term. And the kinetic energy and potential energy on average are equal to each other. And the kinetic energy certainly is a quadratic term, 1/2 mv squared. And therefore, it has an average value of kT. And don't forget to add the potential energy average, which is the same. So it's half of kT times 2. So it's kT. Very simple. This is the energy possessed by each of these oscillators with frequency f. Now, given these 2 results, can we find the total energy of all these electromagnetic oscillators operating between the frequency of f and f plus df within this black body? Yes, we can. It's a matter of a simple multiplication of dn and epsilon bar. And we call the energy stored inside the black body as U. We're looking at du, which is the energy stored in a black body with a frequency range of f and f plus df. And that equals to, as we saw, epsilon bar, the energy of each oscillator, times the number of oscillators, dn. And that's kT times this, 8 pi v over c to the power 3 f squared df. It's just a bunch of constants, whatever constants, kT, whatever, times f squared times df. Now I highlight this because that is only the energy contained within frequency f and f plus df. The range of the frequency, in theory, can go from 0 to infinity. And then we have a big problem. And the problem is, what happens when the frequency is really high? What happens when f goes to infinity? What is the total energy? The total energy, U, contained in the black body, is the integration of du. And that becomes whatever constant times 0 to infinity f squared df. This integral clearly goes to infinity. A finite-sized black body can contain an infinite amount of energy. Now we know this is totally wrong, and this happens primarily because of high frequency contribution. If you look at visible light as a reference, then the immediate region higher than visible light in frequency is called ultraviolet region, and for this reason we say this is called ultraviolet catastrophe. Okay, it's a catastrophe because we're not just getting 30% error or whatever, we get an infinite result, which is totally wrong. This formula that we just derived, it's called Rayleigh-Jean's law. It is a direct application of classical statistical mechanics. In fact, you can move that df down, you get the energy density per unit frequency, and you get kT times a constant times f squared. This expression actually works quite well for long wavelengths or low frequencies. Remember, the problem happens at high frequency range, right? And it deviates from the experiment more and more as the frequency gets higher and higher, or the wavelength gets shorter and shorter. So the problem that we have exists at high frequency, not at low frequency. We'll see in a minute why that is the case. But here's a plot of the Rayleigh-Jean's law versus the actual experiment. So you see, at short wavelengths or high frequencies, there was a major disagreement between Rayleigh-Jean's law and experiment. This red curve is experiment, and the Rayleigh-Jean's law is this blue curve, and the blue curve works quite well. It agrees well with classical physics at long wavelengths. So this is classical. But as the wavelength gets shorter and shorter, the frequency is higher and higher, the theoretical curve and experimental curve start to deviate. The theoretical curve goes up to infinity, giving you an infinite area for integration. But the experimental curve somehow manages to go to a very top value and then goes down, giving you a nice finite integration, which is the total power as a finite constant, which makes sense. So clearly, something must be done to resolve this crisis.